We're going to talk about one-way repeated measures ANOVAs. So when we think about comparing groups who have had a pre and post test, we usually think about a repeated measures t-test, also sometimes called a dependent t-test. But what if you want to look at more than 2 time points? In this case, I have a data set about therapy for children who have nightmares, and I want to look at how many nightmares they had a week, or actually, I think it's how scary the nightmares are. I want to look at this variable at the pre period, the post period, and then a 3-month follow up, and then a 6-month follow up. That would mean I need to use an ANOVA because there's more than 2 variables. So today I'm going to talk about how to do that. So let's look here at our data set, which we can see. Here's our variable view. As you can see, it is quite large. Very interesting study, very detailed. And so let's go to analyze general linear model, repeated measures. So a common mistake would be to go to compare means and do one-way ANOVA here. That's for independent one-way ANOVAs. Since we're repeated measures, we do go general linear model, repeated measures. Okay, so we have to create our factor. So my independent variable is the time points, pre, post, 3 and 6 month follow up. And my dependent variable is how scary the nightmares were, or whatever that variable in that realm may be that I've chosen for this video. And so I'm going to create a factor called time trends 11. Trends 11 is the variable that I'm looking at pre, post, 3-month, and 6-month. And I'm going to say it has 4 levels because it has 4 time points. Then I have to click add. And next I need to define them. So this is a one-way ANOVA. So we're comparing the same subject over time. That means we only have a within subjects factor. Defining that factor, we will want to put the variable at all the time points. The first one was pre-trends 11. The second one I'm looking for is post-treatment trends 11. It can be kind of annoying to find this stuff sometimes. Then we want this 3-month follow-up version. Hopefully this will be easier for you because hopefully you won't be working with a data set this large. And then the 6-month follow-up. We do not have between subjects factors, and we do not have covariates in a simple one-way repeated measures ANOVA. So let's click through the options. Model. We don't need a model. This is what it looks like. This is not relevant to what we're doing today. Contrast. This is not something we're going to change for today. Plots. I like to have it output either line graphs or bar graphs showing the time points. So I'm going to put my factor time trends 11 on the horizontal axis, and there's different things you can do. I'm going to click add plots. In this case, I want to do a bar graph, and I'll include the error bars as well. Post hoc. This is very tricky. This would seem to be where you get the post hoc test. That's only true if the design includes a between subjects factors, a mixed model, only between subjects, something like that. So we actually are not going to use this. EM means, we want to display the means not overall, but we want to display the means for the factor we're using. And we want to compare main effects. That's where our post hoc tests come in. So we can tell, okay, was the pre-period significantly more nightmares than the post-period, the 3-month and the 6-month follow-up, but were the post-3 and 6-month follow-up all the same? So let's compare those main effects, really important. For the confidence interval adjustment, I just do this LSD none, least squares, something, this is the one most people do. I'll click continue. Save. I'm not going to save any of these today. Options. I like to get the descriptive statistics. I would normally like to get estimates of effect size, but in SPSS for this kind of test, the effect size is partial eta squared. Partial eta squared is an effect size that has a lot of problems with it, and everybody uses it, but when you look into the math of how it's computed, it's not necessarily really that good, to the point that I don't even use it. And so I don't really want any of these other things. There's situations where I would if I was very serious about checking assumptions, but in this case, let's just go with the descriptives. Now I'm going to paste my syntax. And so here it is. I'm using a new SPSS feature called Workbook. It's a way you can do your syntax where you have little chunks at a time. They're called paragraphs. You can add a new paragraph, so you can keep running you can keep running little pieces at a time more easily. So let's talk about the output. I am unclear. Oh, it's just really slow. My computer's been really slow today. So, within subjects factors, don't really care about that. Descriptive statistics, I do care about that. Now we have the means and standard deviation for each time point. In this case, they went in order. And so we could see 2.59 nightmares per week in the pre-period, 1.12 post, 0.59 3-month follow-up, and 0.53 6-month follow-up. I am now realizing it was about how many nightmares they had, not how scary they were. However, not really that relevant to a training video. Multivariate tests, do not care about that. Sphericity, do not care about that. There are cases where you would care about this stuff. Some might say I should care about this stuff, but in this video, we're just keeping it basic. So irrelevant. Test of within subjects effects. So here, this is your, well, you could kind of look at this in two ways. I prefer to look at, I prefer to look at it either way. You're having two similar things going on here. So I can see the p-value of the ANOVA here. This is saying there is a significant difference among the 4 time points. And so you want to generally use the sphericity assumed top line of the one under source. The error one, not relevant. So you've got sum of squares, that's not something you would normally report. Your degrees of freedom here is 3 because you have 4 time points. So degrees of time points minus 1 in this case. Mean square, not relevant. The F, that is something you report. And to me, doing statistics for years, that's something I have kind of conventions that I pay attention to. This is a very large F, and ANOVA is an F test. That means it relates to the F distribution. And then we see significance, and this is significant at the less than 0.001 level. Now, it's important to say when we're looking at when we're looking at significance, if the p-value is 0.04 or the p-value is 0.004, that doesn't mean one's more significant, and it doesn't even always mean the effect is bigger. It just really depends, but do not compare the p-value to see the effect size. Effect size is a separate thing. For ANOVAs, it's usually partial eta squared. Partial eta squared is not a good measure. So in this case, we're just kind of looking at it more holistically from the means. Not important. Not important. Not important. Okay, so here are our pairwise comparisons. So in a one-way ANOVA, you would probably use a Tukey test. This is the LSD version, the least significant difference. And so what we're doing is we have a matrix here where we're comparing each time point, 1, 2, 3, and 4, which are in order: pre, post, 3 month, 6 month. And so we want to see where these differences lie. So here we can see we're comparing 1 to 2, 1 to 3, and 1 to 4. And there's a significant difference in all of them. So that means 1 was significantly different. The pre was significantly different than any of the other time points. Here we're comparing, the post to pre, 3-month follow-up, and 6-month follow-up. And what we're seeing here is the only significant difference is between the pre-follow-up and the post with regard to things relating to the post. And as we go down here, what we can see is that the post, the 3-month, and the 6-month follow-up were all different than the pre-measure, but they weren't significantly different from each other, suggesting that gains were maintained over time, which is awesome. That means these kids are having less nightmares after the therapy and then maintaining that gain over time. Not important. But this is a really nice way to see it. Now we can see exactly what we just talked about. We have the pre on the far left, and then you can see the post. And then there's no significant difference between the post and the 3 and 6 month follow-up, but this sample size is only 17, and it's nice to see this trend. If they had more people, you would probably see 3 and 4 being significantly different from 2. So that's more of a statistical power issue. But that concludes what I wanted to talk about repeated measure one-way ANOVAs today. So I hope it was helpful.